again and welcome back to another FMOD and Unity tutorial where today we're creating our own audio visualizers using FMOD to display our music, sounds, dialogue, what have you, visually in a Unity project. This one's quite a fun one because once you understand the basics of how it works, there's a bit going on to kind of understand. And once you get all of that, you can really get creative with it. You can really make some fun looking visualizers and use them for loads of different things. Before we start, as always, I just want to let you guys know that if you need any of the scripts, links to any resources I used in this video, or just help in general with using FMOD, Unity, maybe even a bit of Wise and Unreal, you can come to scottgamesounds.com where you can find extra resources to help you out. You can also sign up to the newsletter and you'll receive a free video from my FMOD and Unity Essentials course. So don't forget to check that out. So what I thought I'd do is I'd not only create my own that you guys can then get from my website. You can copy the script using your own projects, learn from it and fiddle around with it however you wish, but also kind of show you not the entire process of creating it, but show you one particular aspect of it. Now, I'll explain why I'm only showing you that one aspect in a second, but first, let me quickly demonstrate how mine works. So, if I quickly grab my audio visualizer game object, this is the script that you'll be able to copy and download from my website. Again, that'll be linked in the description underneath this video. It's called the FMOD Audio Visualizer. Pretty simple. You give it an event that you want to visualize. Then you select some basic settings, for example, a window size, a window shape, which I'll explain what those do later on. You then find a prefab, you create a prefab that you want to use to control this, or to act as the meters for this visualization. Mine, I'm using this frequency meter here, which actually has another script attached to it. Again, I'll show you that in a second. And again, it will be available on scottgamesounds.com. Then you adjust some more settings. There's a meter intensity, so kind of how extreme or how high you want these meters to shoot up in the air. How far apart do you want them to be in terms of space, because this script is actually going to spawn in the meters. And also a kind of speed setting, so you can kind of slow these meters down or speed them up a bit. So that's how it works generally. Let's quickly play this scene and check out this basic example I've set up. So there you go. So it's pretty simple, as you can see. All this script has done is spawned in, I think 7 copies of that cube, this prefab here. And the cube is basically changing its shape, changing its size, based on the amplitude, or the average amplitude, of each kind of frequency range that I've set to it within my script. So this one here, this first one, is probably about 20 to 60 hertz. That's giving us the amplitude of that. This one's about 60 to 250-ish, and so on and so forth. So obviously you can see here, well, there's a lot of like bass elements in this music. The kind of lower end of this visualizer is popping a lot more, or rather increasing in height more than the rest of them. We can also change some of these settings. So for example, we can increase the meter intensity to about 25, so the meters, or those boxes, will increase higher to display your amplitude. Space between meters, so we can just separate them more, let's say 1.2. The buffer start speed and the buffer acceleration rate. Let's see if we can slow these down a bit. So I'm just going to change that to 1. I'm also going to, oh, not 11. We'll change that to 1. And we'll change this to about 0.01. With the buffer start speed, you have to have really small numbers or it kind of goes crazy. And let's see the difference in our visualizer now. There we go. So you can see the gaps are bigger. It's slowed down slightly. And it's definitely got a lot bigger. So you can kind of adjust things to make it, fit whatever scene, or however you want, basically. Now you may have noticed there's also this little FPS counter. Now I thought this is just a little bonus I added. I thought this might be handy because sometimes when you increase the window size, again, we're going to talk about that later on, the performance of your game can actually start to suffer if you increase it too high. So I thought that was just a handy little thing to have, so you can actually see the effect your settings in the audio visualizer are having on your game. So for example, if I set this to about 512, let me play the scene for you and we'll see the performance, or the effect on the performance it has. So we look at the FPS counter. Oh, that isn't good. We're on about 20 frames a second, and you can also kind of see, oh look, if I move the camera around, oh dear, the game is not performing very well indeed at all. So if I drop this down, say to 128 and play it, oh, let's have a look at the difference that makes. Oh, there we go, much better. So it's a lot smoother to move around. We're getting a much higher FPS rate. About 43, 44 frames a second. Oh no, it's gone up. Still, it's not quite 60. It's not quite ideal. So we can lower this even more. I'm going to be a bit drastic now. I'm going to lower it to 16, and you should notice a difference that happens in the actual analyzer. So you can actually see now that there are only 4 meters that our audio visualizer is displaying because we've reduced the window size, which again helps the frames per second, the performance of the game increase. The reason why it's now reduced the amount of bars is because those bars, like I said earlier, represent a range in frequencies that they're then displaying the amplitude of. So for example, that first bar originally was displaying about 20 Hertz to 60 Hertz. Well, now because we've reduced the window size, we're kind of increasing those frequency ranges, or rather we're taking sort of more, or sorry, we're taking less snippets, less samples of each a range amount, I suppose. Originally we were doing lots of small ones, now we're doing few larger ones, if that makes sense. Because of that, it can't display as many bars because it's got less samples, less information to display, to use. So that's why it kind of compensates for that by reducing the amount of meters it displays. But anyway, yeah, I think I've covered everything on my audio visualizer. The last thing is just the play on awake function. So if you don't want the music to play straight away, you can just untick that. And you can actually, there's a function in this script that I think it's just called play FMOD event, that if you want, you can call from other scripts. So if you wanted something else, some other condition in your game to trigger this, you can just, you know, set up a script and call that event. Or sorry, that function. But we're not going to talk about it in this video. Like I said, this is just for you to mess around with, have some fun. So go to scottgamestills.com where you can copy this script and you can just stick it in your own projects and mess around with it. Add some different FMOD events to it. Actually, I don't think I explained this bit, did I? So there's an option, there's a part here called event path. It's assuming you've got an FMOD project kind of imported, assigned to a Unity project, you can then use this to search through all of your events and pick one to display. And also, as well as that, let's quickly show you the meter objects I'm using. So it's just a cube, basically, that I tried to make shiny and flashy, but it didn't really work. But it doesn't matter. Let's quickly close all these extra components. So these are standard components. You've got like a box collider, mesh renderer, etc., etc. Param cube is the one I've attached, and these, it just gives you some options to set the scale and the size of it. What my audio visualizer does, it actually searches for this script, and using this script we tell the box to basically increase its scale within the y-axis. Okay, and again, both the, well, I'll have a look if I can upload a prefab to my website. Hopefully I can, but if I can't, at the very least you'll have this script that you can use and just stick on a cube or something. And again, have some fun with, do whatever you want with it. But now that we've seen the audio visualizer in action, it's time to look at that aspect of it that I want to show you guys. Now, when it comes to taking samples from digital audio, I learnt a lot from another YouTuber who does a lot of audio stuff with just Unity without FMOD. Now that YouTuber is called Pear Play, and he's got loads of videos on this topic, audio visualization. In fact, here you're looking at a great playlist, to be honest, to learn about all this stuff. Not only does he show you how to set it up in a basic sense like I've done, but he gets, towards the end, he gets really creative with how he displays his audio. Now the particular video, basically what I want you to do if you want to learn how to set up audio visualization with Unity is go through this playlist that I'll have linked under this video and get to this one here, audio visualization, part 2, get spectrum data in Unity. What I'm going to do with this video is essentially create a replacement for this video if you wanted to do this exact same thing, but with FMOD instead of just Unity's audio engine. In this video, he basically talks about a function that Unity provides for you that allows you to get what's known as spectrum data from any piece of audio that you're playing. Obviously, we're not playing it through Unity, we're playing it through FMOD, so we need to get that spectrum data ourselves using FMOD's API. So definitely go check out his videos, send him a load of support, because I was watching some others and they're really fantastic. He goes into, he's taken a lot of time for these, so he's definitely worth the love. But with that said, let's jump into the script I've created that, like I said, replaces this video, or replaces the method he uses in this video. So the script I was just showing off was called FMOD Audio Visualizer, but what I want to do now is show you this script, get FMOD spectrum data. Because using this script, I created a new method that basically replaces the get spectrum data function that Unity provides for us, and obviously allows us to get spectrum data from an FMOD event instead. Now I've just brought up the video in question and I've skipped right to the end to kind of show you what he does in this video. What he's doing is he's playing some music and he's got loads of spectrum data basically, and he's putting it into a float array. So what he's doing is he's getting loads of values, and all of these values represent a value or an average of the audio's amplitude within a specific frequency range, okay? Okay, so here is just a bog standard picture of a frequency analyzer that you'll probably find in most DAWs. I'm sure you're familiar with them if you've ever used a DAW before. Yeah, like I said, this is just basic, showing you the kind of frequency ranges you would be aware of, I suppose, if you were mixing music, right? The common ones are like your low end, your low mids, mid-range, and so on. Now, what I'm about to show you in Pearplay's video is what he does is he takes this kind of frequency spectrum of the music he's playing, and using the script he's created, he chops it up into samples, right? And he chops it up 256 times, okay? Then what he does, so each of those samples he's, made from he's chopped up from his music. Let's say it's kind of hard to see, but this, between these two vertical lines, is one sample, right? What he would do is he is basically taking the average level of amplitude for that frequency range, right? And he's doing that for each sample. Then later on, what he'll do using that is he'll kind of combine some together and use that to control the level of his cubes, basically. That, obviously then represent the amplitude of the audio. So now that we understand what he's doing, let's quickly play. Just this, what I'm going to play you is just the end section of his video that we're kind of replacing. So you can kind of see his end result from that video. Now, it's kind of hard to see, but you can see, oh, and actually it wasn't 256, it was like 512. But you can see all these numbers here, these all represent those samples I told you about, and its amplitude. So if we go back to our picture, 512 times he's taken like a sliver of the frequency range. So like the first one's probably 20 to, I don't know, 48, and then 48 to 60 something. And he's getting the average amplitude. So yeah, now that, and then he goes, like I said, in the playlist, he goes on to use those numbers to create his visualizer. But the way he did it, in fact, I might even be able to find it. There it is. Okay, so he's used this function here, get spectrum data, and he's using that off the audio source, the Unity component, which plays sound that he's attached to his game object. And what he's doing is he's giving this function an array, which, if you don't know, is basically just a list almost. It's like a collection of lots of data types. So we know how we have the float data type, which takes numbers with decimal places. We have integers, which takes whole numbers, and we can create variables to hold things within those, or using those data types. So we could create a variable. We could call it, say, I don't know, height, for a player's height. We could set it to the float type, and then we could store a number within it. So that number could be, say, 5.6, so that our player is 5.6 feet or meters. Well, maybe not meters, that's crazy. But you get what I mean. A variable of a certain data type can hold certain data. Well, an array kind of holds multiple different copies or multiple different pieces of data for that type. So an array of the float type means you could hold multiple different numbers. So 5.6, 2.8, 7.7, and so on. He's called his samples because, again, he basically just wants a list of samples that, again, if I go back to our handy dandy picture, are sampling the kind of ranges within a specific frequency and getting the average amplitude. I've lost the video now. Whoops. There we go. Yeah, so what he's doing is he's basically using this function to analyze the music he's playing and take all those samples and give him numbers and put them inside this array here called samples. He set the size of the array to 512, meaning that there's 512 slots that he can put those numbers in. Like I said earlier, he's chopping up that frequency spectrum into 512 slices. So that's, you know, each one represents the amplitude of a frequency range. Now you can see at the end here, he's written something called FFT window.blackman. Now when it comes to analyzing audio or spectrum data in general, due to the methods that and the kind of maths behind it all, some of the data you analyze and therefore, you know, some of the frequencies can be lost. Which is obviously not ideal, but there are different kind of methods, I suppose you can call them, different options, different window shapes that you can select from to reduce the amount of leakage and therefore data loss. And it kind of depends on the audio you're playing it for. You know, there's like 5 in general, and one might work better for you than another. But what's lucky for us, if we go to the FMOD documentation, they actually have some examples of what these look like. So the 5 examples, actually there might be 6, but the main ones are called rect, triangle, hamming again for some reason, Blackman, Harris, and that's it, okay. And if we go back into my project, you can actually see an option to select the window shape that you'd like to use to analyze your audio with. So again, rect, triangle, hamming and hanning, that's the difference. Blackman and Blackman Harris. And yeah, give that a read. I'll have this linked in this page from the FMOD documentation and the description of this video. You can kind of get a better idea of the differences between them. But anyway, that's enough of looking at pair plays videos. It's finally time to dive into the script I've created for you that I want to explain. Like I said, okay, actually I lied. One more time. Let's quickly, one more time, have a look. The idea is, for this video anyway, is we just want to create the exact same setup he's got. We just want to create an array and get the sample data for each kind of frequency sample for our audio, okay? So we basically want an array that looks like this, that we can see all the numbers pop up and fly up as we play our audio. So if I go into Unity, let me quickly play this scene and, you know, using this script now, not the audio visualizer. I'm gonna play some music and we should see the same thing happen. This, as you can see, I've got an array called samples. What will happen when we play it is the size will pop up depending on the window size we've set, and we'll see all the numbers for our music and the, you know, the amplitude for each sample. There we go. See? So we scroll down. So these first few pieces of our array, they're low numbers, as you can see, it's 0.0 whatever. But because this is all representing kind of the lower frequencies, let's go to our little diagram again. Oh, where is it? They're all sort of representing the low end, and because this is quite a basic song, they're going to be higher than, if we scroll down, these lower numbers in the array. So as you can see now, they're like in the E-6, which means that it's like 0.06 times before you actually get some numbers. But yeah, once we understand how this works, you can then continue following on Pair Plays videos to get really creative with actually how you display all those samples. So enough chatting, let's jump into this script and see how it works. Okay, so what we're going to do, this is the script by the way, what we're going to do is we're going to work our way down this script and try to understand it the best we can. I'm going to start with the variables. I'm going to explain kind of their role, why they hold the data they hold, and then how, after that, we're going to talk about these functions I've created and what they do with that data in order to get us all those numbers. Okay, so the first one is a public string, which means it takes just characters and letters, and I've called it underscore event path. By the way, I've called all my variables, well, I've started the name of all my variables with an underscore just so we know the variables that, you know, I've created and, you know, bits and pieces of the code that come from elsewhere. Say, for example, FMOD's API or Unity's API. So, like I said, it's a public string, meaning it holds characters and letters and numbers, and I've called it event path. Now, this is basically going to hold the event path for FMOD. I've talked about this before in plenty of other videos on this channel. Whenever we want to get an event from FMOD, this is the event, by the way, I'm playing, we need an event path, and the event path is basically just where it's located within your project and your project's folders. You can just type it out here. You can go blah 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 event wherever, or you can use or you can use this. You can add this attribute to the beginning, so you can actually select the event within Unity's inspector. So you just write fmod unity.eventRef in front of it. If I go back to Unity, you can see it here, event path, and it gives us all these extra buttons. That's what the attribute does. It gives us these extra buttons so we can just quickly search for the event we want to play. It also it's great for an audio visualizer because it allows us to quickly change events to test the audio visualizer with. So yeah, that's definitely worth doing. The reason why I've just set it to null at the beginning, which by the way just means that this variable is empty and not holding any data, is just to get rid of that annoying message you sometimes see in Unity's console where it goes, "Oh, this variable doesn't have any data in it," and it's like, chill out, mate. I know I'm gonna add some data later. It displays that because it thinks, you know, as you're starting this scene, there's no data in it, even though you're probably going to add data in it later. Anyway, it doesn't matter. That's the only reason why I've added null. It's just to get rid of an annoying message that Unity pops up for us. Moving on, the next public variable that we've got to display in our Unity inspector with is called window size. Now, this basically kind of determines how many, there's more to it than this, but it determines how many samples you want to take of your audio, right? So again, like I said in his video, he used 512. If I go back to this, as I explained right at the beginning of this video, you can reduce that number. So you take basically, so the sample sizes, say this is one sample, will go from smaller ones and lots of them to bigger ones and fewer of them if you decrease the window size, okay? So you're taking less samples, but the samples are actually bigger. Now, one thing to note about the window size is that it has to be to the power of 2. Specifically, when using it for FMOD, it also has to be to the power of 2, but also it has to be between 128 and 16,384. No, that was wrong, 16,384. Now, this variable is of the integer data type because it takes whole numbers, okay? And that's pretty much all you need to know for now about the window size. Next is the window shape. This goes back to what I was explaining earlier, the different shapes. Oh God, I've lost it. Here we go. The different shapes you want to use when capturing your data, your frequency spectrums, so you don't get any leakage of data. For FMOD, there is a specific data type for this. The data type is actually an enum. Enumerators basically are like predefined constants that represent a value. So this enumerator is, they've called it DSP_FFT_window. And within it, they've created constants for us to pick from. Those constants that they've chosen are the names of all these windows, so rect, triangle, Hamming, and so on. So what we need to do is give this enumerator one of those constants. It will then take that constant using some magic FMOD API code. It will then be able to say, oh, okay, he wants to do this with his audio. He wants to, you know, use the Hamming window shape, for example. We don't really need to worry about the back end too much. We just need to know how we set a window shape, basically. So we do that by writing FMOD, because this enumerator belongs, it uses the FMOD namespace. Basically, there's a script that when you install, or rather when you integrate an FMOD project with a Unity project, doing that, you're actually also downloading a load of scripts, kind of like the script we've created here, except the script was created by the FMOD developers, okay? In those scripts, they use namespaces. Not really going to talk about what namespaces are too much, but basically to access certain information from those scripts, we need to use certain namespaces. To access the DSP_FFT_window enumerator, we need to include the FMOD namespace in front of it, okay? So that's why I've written it in front of it there and there. But anyway, whenever we're trying to set a window shape, we need to write fmod.dsp_FFT_window, God, that's a mouthful, followed by the name of the window shape. So as you can see, I've just defaulted it to rect. Again, this is something you can change in Unity's inspector, but if we wanted to change the default, I could just remove that, add a dot, and you can see the list of options we've got here, okay? I'm just going to keep mine as rect for now and save it. Cool, so those are the public variables that you could choose and you can change in Unity's inspector. Now let's move on to some private ones. The first one is an event instance. This we've covered quite a lot on this channel. Event instances are just copies of your event, because obviously if you wanted to, you could play loads of copies of your event. If I go back to if I go back to FMOD, if I wanted to, I could create loads of copies of this event and tell them to play at different times or do whatever with them. Maybe I wanted to add a different effect to each of them, right? We only want one instance, one copy, so we don't have to worry about that. But in order to get that copy, we have to create a kind of variable of the FMOD Studio event instance type, which we can then store a copy of our event inside of. Then once it's inside of it, we can tell it to play, we can tell it to stop, we can do whatever we want, okay? So that's what I've done here. Again, FMOD Studio namespaces, the data type is event instance. Technically it's a struct, but I'm not going to talk about that in this video. And I've called it _event, okay? That's just all you need to know about that for now. Next, we have something called a channel group. Now, we haven't talked about channel groups on this channel yet. Channel groups are interesting. They actually, what they allow you to do is monitor the signal of an event or a bus or whatever really within an FMOD project. Within the hierarchy of your kind of signal flow in FMOD. So let's go back to FMOD quickly. And in fact, let's go to Window, let's go Mixer. Now, this is a very simple project. There's barely anything going on. There's a sound effects bus with just a footsteps event going into it. And obviously there's a master bus. This is the sound effects. Oh, there's also, sorry, a return reverb bus and a master bus. There's not much going on, right? What you can do with channel groups is you can basically use them to just measure basically the either the input or the output any of these channels are receiving. You could attach it to an event, for example. I could attach it to this talking to event. I could use it to monitor the input or the output, or I could attach it to a bus. So I could attach it to the sound effects bus, measure its input or output. I can even attach it to the master bus if I really wanted to. So it allows you to kind of measure levels, essentially. Now you can use this if you want to get the RMS or the peak levels of an audio event or just audio in general from an FMOD project, but that's not what we're going to use them for in this project. What we actually want to do is attach or create a DSP, which stands for digital signal processor, to a channel group, which we can then use to do what we're going to do in a bit. Hopefully that makes sense. So really the channel group, we're not doing it to measure the levels, we're doing it to attach something else to it. Obviously the event I'm using for this demonstration is called visualization. So what I want to do, in fact, let's get out of this window. Let's go to event editor. Here we go. So what I want to do within my code is kind of attach a channel group to my event, or my event instance specifically, use it to measure the output, or rather, sorry, not measure the output, use it to then add a digital signal processor to, and then using that digital signal processor, I can get specific information from the audio, from the signal that's flowing out of this, or out of the copy of this event, okay? Hopefully that makes sense. So that's what the data type channel group does. Again, it's a struct, don't worry what that means. And I've just called mine _channel group, okay? Nice and simple. Then underneath that, we've got a variable of the DSP type, again using the FMOD namespace, and I've called it DSP. Now this is what I was referring to, a digital signal processor. So this can hold different types of, well, digital signal processors. So for example, you can turn this into an EQ, you can turn it into a compressor, reverb. It's a way of kind of attaching effects essentially to an event within your code without having to use, if I quickly jump into FMOD again, without actually having to use FMOD. So maybe, I don't know, halfway through your game, you can program it so that if a certain event happens, you maybe add a reverb, say, onto an event. You can do that using DSPs. Now, underneath that, we have a variable of the DSP _parameter _FFT type. Now, this is something very specific. Basically, like I said earlier, you can create DSPs, and you can create DSPs of different types. By type, I mean it could be an EQ, it could be a compressor, whatever. The type I want to create this or turn this DSP variable into is an FFT. Now, FFT stands for Fast Fourier, I think that's the name of it. Fourier? It's this word here, however you pronounce this word. Fourier transform. And it's kind of, again, it's a method of analyzing digital audio, right? It's actually really clever. I'd highly recommend this video by 3Blue1Brown. I've just got in the background, I'm not going to play the audio. Anyway, he explains it very clearly how you can kind of measure the sine waves. And in fact, you can actually take multiple different sine waves, combine them together, and that's how you get that kind of shape that you see in digital audio, right? And this is kind of what he's explaining here. Yeah, so it's kind of it's a method of basically taking a digital signal that's got loads of different noise, sounds, etc., which creates a kind of messy sine wave, taking that, dissecting it into multiple more smoother signals, and then using that to do whatever you want. In our case, analyzing spectrum data, right? So definitely check that out if you want to understand what fast Fourier transform actually is and means. Highly recommend it. Okay, so going back to our script, within FMOD you can basically create lots of different variables of different DSP parameter types for specific, well, types of DSPs basically. So say for example, I wanted to turn this DSP into an EQ, well I could create a parameter of probably the DSP parameter EQ type, right? And then using that, we can access different information specifically for an EQ, so say a particular band size, for example, right? So for FFT, we want to create a parameter of the DSP parameter FFT type so we can access specific information in relation to FFTs. Now, if we go to the FMOD documentation, we've got this page, and this basically breaks down the different information you can access from a DSP if it is of the FFT type. You've got the length, you've got the number of channels that's being sent to it. So for example, a mono would have 1, stereo would have 2. Spectrum, that's what we're interested in, but we're going to come back to that later. And some other nonsense that we don't care about. And these are important to know. As you can see, it kind of gives us a brief description of them here. It's also important to know that these have indexes, and by an index, I basically just mean they're ordered by numbers, basically. So the first one you can see here is represented by the number 0, that's index 0. The second one is number 1, number 2, and so on, okay? So if we wanted to access, say, the number of channels within an FFT, we'd have to say, use this parameter and access index number 1, okay? Because even though it's the second one in the list, indexes always start at 0, okay? Hopefully that makes sense. Again, this page will be linked in the description for you to check out. And the last variable is a public float called _samples. This is basically the exact same thing. Oh, I think I got rid of the video, didn't I? Give me 1 minute. There we go. So this is the thing that's basically going to hold all of our numbers, all of our different samples of our audio and the amplitude levels. So if I go back into my Unity project, it's this here, which is also public. The size of it basically sets how many, well, how big is the array? How many pieces of float data do you want? It's starting at 0 within Unity's inspector, but don't worry, as we get into our script, we're going to set its size later on. Cool, so those are all the variables. Before we continue, it's getting a little bit dark where I am, so give me 1 sec, I'm going to quickly fix that now. There we go, much better. So now that we've looked at all of the variables, let's have a look at the functions. And as always, we're going to start with the start function and then move on to some custom functions and the update function. So as we know, the start function runs as soon as this script and the game object it's attached to is active. Within our game, on the very first frame, it then does whatever we tell it to do. So what I'm using the start function for is 2 things, is to basically call this function here that I've created, called prepare FMOD event instance, as well as also set a size for the array that we looked at earlier. So let's first look at the prepare FMOD event instance function. So this function is basically here just to set up the event and also kind of arrange the DSP and the channel groups that we talked about earlier, get them all working the way they should so that we can then use them later on when analyzing the spectrum data for our audio. So as always, we start by creating an instance of our event. So what we do is take our event instance variable, which remember I called _event, and we write equals fmodunity.runtimemanager.create instance. Then in the brackets at the end of that line, we need to give it an event path, which needs to be in the form of string data. Now, as I mentioned earlier, you can just write that out with, just string data in text, but we can also use the event path string variable we created earlier. So that's where that comes into play. Next, this is optional. This is assuming that you might want to use a 3D sound over a 2D sound. Now for this, I'm just using a 2D sound, so I don't really need this line here, but I've added it because it's nice to be able to switch between the two for this audio visualizer. For your purposes, you might want to use it for 3D or 2D events, not too sure. So if you do want it for 3D events, you'll need this line here. So what I've done is I've taken our event instance variable, which now has an instance of our FMOD event, this one here, stored within it. So if we ever want to access the copy of this event, we do that by accessing the event variable, okay? So we write that, then we follow it with .set 3D attributes, then we create two brackets and we write FMOD Unity .runtime utils .to 3D attributes, then we add two more brackets, and then we basically say at what position we want to set this sound to play at. So for 3D sounds, there is a bit of pan and volume attenuation depending on the location of the sound you want to play your sound at, and the location of a studio listener component that comes with FMOD. Now actually I'm not sure where I've put my studio listener component in this game. I imagine I've added it to the camera, which I have done. Okay, so the difference in pan and volume will depend on the distance between my camera object, which as you can see in the scene tab is there, as well as the object that I'm playing my event at, which is here. Yeah, so that's pretty easy stuff to understand. You move them around and you're going to get different volume and panning attenuation. And of course, if I jump into FMOD, if I actually select a 3D event, because that one wasn't, here we go. So this is a 3D event, this talking event, because it has the spatializer component attached to it. Now we can make adjustments to this, so we can adjust the min and max distance that controls the volume, attenuation basically, the roll off. But yeah, like I said, I'm just going to focus on this 2D event for now. So let's go back to our script. Yeah, and if you wanted to play this at a different location, you can. By writing GameObject.transform, I'm simply telling this to play my sound at whatever location the game object that I've attached the script to is at, which in this case is this location here. Bit of a mouthful, this line, I know, but it's one of those lines that's worth kind of writing down to remember. Anyway, once we've got the instance of our event and we've positioned it in our world, all that's left to do is tell it to play. And we do that by writing _event.start. Okay, so we've got the event and the event is now playing in our game. But now we need to do some stuff with the DSP and the channel group variables we created earlier. First thing I want to do is kind of set up the DSP variable. At the moment, it's just an empty variable that's not really doing a lot, okay? So we need to change that. Now remember earlier I mentioned about DSP types, and you can create a DSP variable and assign it a type depending on the effect you want to give it. So for example, an EQ, sidechain compression, whatever. Well, using this line here is how you do that. So to basically create a type, you have to write fmodunity.runtimemanager.coreSystem.createDSP by type, and then inside the brackets that follow, you declare the type you want. Bit of a mouthful, I know. Now within the brackets, you need two arguments. The first one here is the type that you want to set your variable to. Now there's lots of different types. To declare a type, you write fmod.dsp_type followed by the type. But if I quickly remove the type I've gone for, which is FFT, and just press dot, we should be able to see all the different types. So here you can see we can create a DSP for adding a chorus effect, delay, echo, that's just one for a standard fader, that's the FFT I added earlier, flange, high pass filters, and so on. So just scroll down and have a look at whatever effect you want to add. But like I said, FFT is the one for me. That was awful. Yeah, so that's the first argument. The second argument, which you add by separating it from the first with a comma, is basically tell it, okay, well, which variable are we giving a type to? Which DSP variable have you created that you want to assign this type to? Because really, if we wanted to, we could create loads, couldn't we? I could copy, paste that, and give this, a different name. So it needs to know which variable, it wants to turn into a DSP of the FFT type. So to do that, we write the keyword out, because we're kind of outputting this information to the variable, and then we follow it up with a variable of the fmod.dsp type, which of course for me is _DSP. Great, so now our DSP is of the FFT type. Now before we continue and move on to these two lines here, which is where I'm kind of setting parameters, I want to quickly open up a page from the FMOD documentation. Okay, so what you're looking at now is basically a page from the FMOD documentation where they describe the parameters that are associated with a DSP if you set that DSP to the FFT type. As you can see, they are window size, window type, spectrum data, and dominant frequency. Now, just like with the, they're in the form of an enumerator, as you can see here. which remember is basically a list of constants, names essentially, which are these names, that the FMOD developers gave particular values, which then, when called upon, do particular stuff that we don't have to worry about. So just like with the window shapes, these are all listed in order by their number or index. So starting at 0 for window size, window type is 1, 2 for spectrum data, dominant frequency is 3, okay? Now, whenever we want to set values to these parameters, for example, we might want to set a particular window size. So as we discussed earlier, we might want to set a high number so we get lots of data back, lots of samples, or a low number so that the performance of our game works well. We need to call whichever one of these parameters we want by their index number. So if we go back into the script, you can see that's what I've done. First we need to use a particular line of code, a particular function to access a parameter within a DSP type. So to do that, you get your DSP and then you write .setParameter integer. The reason why we're writing integer is because, again, like I said, all parameters within DSPs are ordered within an index, 0, 1, 2, 3, 4. So obviously integers are a data type that can only be given, used, whatever, in the form of whole numbers. So again, 0, 1, 2, 3, 4. So by setting a parameter integer, we're essentially setting a value of one of our parameters and telling FMOD's API in Unity which parameter that is we're setting a value to by its integer. Let me explain what I mean. So as you can see, I've written this function out twice because I needed to use it twice and set the values of two parameters. The first parameter I wanted to set is the window type. Now the window type, as we looked at earlier, is an enumerator, right? So it's window size, window type, blah, 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 blah. It's not actually in the form of integer data, despite the fact it's kind of listed within, it has indexes and, you know, like I said, it starts from 0, 1, 2, 3, 4. That's the order of those constants. And this parameter, or sorry, this function, for its first argument, as you can see there, with that little grey box that's popped up, it requires an index in the form of an integer number, okay? Now, if I were to remove this little bit here that says int in 2 brackets and just write window type, telling our function which parameter within our list, oops, let's get rid of that, which parameter in our list that I want to access, it's actually going to give us an error, as you should be able to see by that red squiggly line that's appeared. And again, this is because it only accepts this data in the form of an integer. Now, let's go back to our list. As we can see, window type is the second one within this index, within this list of constants. So if I wanted to access it, I could just write the number 1, because again, we start at 0, then 0 is the first thing in our list, then number 1 represents the second thing. So I could just write 1 there, right? And that would be telling our function that we want to access the window type. Or we could do the other way, which I've done. Let me go back a few times. We could actually write window type and we can convert that into an integer, right? So this is called typecasting, where you've kind of got a piece of data in the wrong format, but you cast it into another format. So a common one is, say, I'll tell you what, I'll quickly make an example for you. Let's say I created an integer variable, okay? And I just called it thingy, right? And I wanted to give it some data, right? But let's say for whatever reason, the only data I had to give it was data that is being stored within a float variable. So I'm going to call this other, right? And I'm going to set this to 3f, right? So obviously I can't set the value of thingy to whatever the value of other is, because other is a float and thingy is an integer. So where other can, if we wanted to, have decimal places in its value, thingy can't, because it's an integer. Well, to fix that, we can actually cast the data type of our other variable into a different data type just for the thingy variable to use. And we do that by adding, not the number 90, by adding 2 brackets in front of the variable and then writing the type of the type of data we want to cast it into. And there you can see now the error's gone, and the thingy variable is quite happy to accept the data from it. Now I believe I couldn't set this to say 3.3, or maybe I can, the error's not appeared. But obviously, like I said, integers don't accept decimal places. So it's possible that either this will be rounded down to 3, a value that the integer variable thingy can accept, or maybe we'll just get an error in Unity. That's something I'm not actually tested, but hopefully that makes sense. You can typecast variables into different types to kind of convert them, okay? Okay, so that's basically what we're doing with the set parameter integer function. Window type is the value, however, it's part of the DSP underscore FFT enumerator, and our function doesn't accept that, it only accepts integers. So we're simply casting it in the form of an integer, and by doing that, it's taking the index of window type within this list, which is 1, okay? So that's so by doing this, we're telling our function that, okay, we want to set a new value to the window type of our FFT. What value do we want to set it to? Well, that's where this half of the, or this argument comes into play. So again, we're doing a bit of typecasting here. We're turning it into an integer because again, that's what this function accepts for the value we want to set it to. If we go to window shape and scroll up again, as you can see here, this variable is of the DSP underscore FFT underscore window enumerator. Now that's not to be confused with this enumerator here, the DSP underscore FFT. Very similar, I know, but they're different enumerators. If I quickly hold Control and click on this enumerator, you can see this has different values. Each of these, window shapes are the values that we can choose from for this enumerator. Whereas if I click on the DSP underscore FFT, these are the different values. We've got window size, window type, all the basic parameters basically of a DSP of the FFT type, right? So again, we need to do some conversions. We want to take whatever value we've set to our window shape variable, which at the moment is just defaulted as rect, and convert that into a value. So let's go back, let's have a look at the options within our enumerator. So again, they're all indexed. Rect is 0, triangle 1, hamming 2, so on and so forth. So those numbers kind of represent those values. So in the case of this defaulted value here, rect obviously would be the equivalent of, say, 0. So if I scroll down, if I just wanted to set this to rect and not give myself the option to change it later within Unity's expector, I could just put a 0 here, right? Or maybe I could put a 1, I think that was triangle, wasn't it? A 2 for hamming. I think 4 was black man, and so on. You get the idea. But instead, I'm taking whatever value I've assigned to window shape, and I'm typecasting it to an integer. Okay, so now, despite the fact I've set my variable to the value of this, rect, basically, the value we're giving this function is 0, which is something it can work with, okay? Cool, so this line here, basically, is taking our DSP of the FFT type. Within it, it's taking the window type parameter and it's assigning it whatever value we've set the window shape variable to, which at the moment is just 0, the rect shape. Next thing we need to do is assign another parameter of value within the DSP, but this time it's the window size. So again, we write underscore DSP.set parameter integer. Again, we choose which parameter we want to set a value for. This time it's window size, but again, if we were to just write window size like that, we'd get an error because it's not an integer, it's a value within this DSP. So we typecast it to an integer, which this time I think, let's quickly have a look. Window size, okay, so window size is the first one on the list. So another way of writing this would just be to write a number 0. And then the second half is the value we want to set that parameter to. This time, let's scroll up. So this time we're using the window size variable. Thankfully, window size is already an integer, so we don't have to do any typecasting here. What we do have to do is, what I've done, as you can see, is I've actually multiplied the window size by 2. Now, within our script, we're using the window size to basically set how many samples we want to take or analyze from our audio, okay? As you can see here, there is a formula for doing that. The amount of bins they refer to here, but by bins they basically mean those chunks, those strips, or those vertical sample amounts. That is equal to the FFT size. And if I quickly go back to my script, again, that's what was those numbers I mentioned earlier that have to be to the power of 2. You take that and you divide it by 2, and that's how you get the amount of samples, okay? Now this could be a little bit confusing, but hopefully what I'm about to do will help make more sense. So let me just quickly remove this part here where I multiplied by 2 and save my script. And go back into Unity essentially and show you what happens. Before I do, just note that the size of my array, so the amount of slots within my samples array that I can store our samples in, and the amplitude value that they hold, I've set to the window size, right? Now in Unity, I've set the window size to 256, okay? So we're going to have 256 slots appear. Now, the parameter, the window size, I'm setting to just the value of my window size variable, which again will be 256. However, notice what happens when I don't multiply it by 2 and play my scene. Okay, so if I scroll down, so we get about halfway, as you can see, but now we've stopped, we've run out of data, okay? So whilst our array is still 256 slots in size, we're only getting about half of that, 126-ish, 125 pieces of data, right? So if I go back to our little diagram, this spectrum graph, the audio basically, frequency range is being split up 125 times. Now to be honest, I get a little bit lost with the maths here. You'd think it would just be 256 because that's the value of the window size variable. But for some reason it's not. As you can see by this formula, let's zoom in a bit because it's a bit small. Not that much, there we go. As you can see by this formula, the amount of samples you get are or equal to the FFT size divided by 2. So if we want 256 samples, then we have to take our FFT size, if it is of 256, and multiply it by 2 to get 512. Else, we'll be getting 125-ish samples, which obviously isn't as much as we want, okay? So just to keep the two consistent, the sample size in control of the amount of samples we actually get, we times it by 2. I don't know why, don't look at me, that's just how it works. And again, like all the stuff I'm showing you in this video, this article will be linked in the description so you can learn more about it. Maybe even understand it a little bit better than I do. Okay, cool. So we've got a DSP. We've set its type to FFT. And not only that, we've taken the two parameters, window size and window type, and we've assigned values to them. Spectrum data we're going to be looking at shortly, and dominant frequency we don't need. The dominant frequency just tells us which frequency in our audio is the loudest in amplitude, okay? For what we're doing today, we don't really need to worry about that. Cool, so moving on. Now that we've got all that information, we need to go back to our channel group. Remember that variable we created earlier? Well, we've got that variable, but it's kind of empty and it's not really doing anything. So we need to basically attach it to an event, or rather, actually, I suppose what we need to do is the other way around. We need to take an event and we need to output its data into that channel group, right? And we do that with this line here. We take our event instance variable and then we use .getChannelGroup. Then within the brackets that follow that, we write out underscore channel group. So again, we're outputting data from the event. In fact, let's go to FMOD. So I believe it will be the kind of signal, and the data that flows from that signal will be outputted, basically the end of your chain if you were to add like loads of effects. All of that will then be stored within underscore channel group, okay, the variable we created earlier. Then after that, one final thing to do, we want to add our DSP to that channel group. And we do that by taking our channel group variable, using the add DSP function, and then we give it two pieces of information. The first is another index. Basically, you can add lots of DSPs to a single channel group, right? Which makes sense. So kind of in which order do you want to add them to? And again, you do that with a list of indexes. So 0 being the first, 1 being the second, and so on. Seeing as this is the only DSP I want to add, I'm just making it the first in my list, which is 0. And then you need to tell it which DSP variable you actually want to add, because again, we could have multiple DSP variables. So I just wrote the name of my DSP here, underscore DSP. Okay, cool. So that's pretty much everything to do with prepare FMOD event instance. So quick recap on what this does. We've created a copy of this event here. We've set its 3D position coordinates within our game world, which is just matching the game object that this script that's calling it is attached to. Then what did we do? Then separately, we took our DSP variable, which was not doing a lot. We set it to the FFT type. We then took the window type and the window size parameters within that DSP type to, I can't remember what values we set it to now, to rect and to 512, which again we can change within Unity's inspector. Then what we did is we went back to our event instance, we took a channel group, and we basically told it to measure the data flowing from the output of this event. And then we added that DSP we created earlier to that channel group. So now all the audio and all the signal that flows through our event to the output kind of channel of it into our channel group will then also go through this DSP, which we can then use to monitor spectrum data with later on. And by assigning values to the window size and the window shape, we'll get specific amounts of data, if that makes sense. So we'll get, like I said earlier, we can get 128, 100, or sorry, 200 and, I'm forgetting the numbers now, 256 amount of samples and so on. Cool, so now let's go back to the start function. So that's the first thing that all of that happens on the first frame. It happens once and as soon as our game starts, okay? Then after that, we set, or what I'm doing is setting a size to my array, okay? And I quickly mentioned this earlier. So I took my array, which is underscore samples, and I wrote equals new float. Then I took 2 square brackets, and then inside that is the value I want to use to set the size of my array. So again, the amount of slots within my array that I want to store data in. And basically, because I just want this array to hold all of the samples that I'm taking from my DSP, or from the event using the DSP, obviously that DSP we've set a size for, so that is 256 in Unity. So I'm basically going to want this to match that size, right? Because if I'm slicing this audio up into 256 pieces, then I need my array to hold 256 pieces of information, okay? Cool. Okay, so moving on, if we scroll down, we can see underneath the prepare FMOD event instance function, we have the update function, which we know will run or do whatever we tell it to on every frame of the game, or every frame that this script is active for during runtime of our game. Now inside the update function, I'm simply using it to call the get spectrum data custom function I've created, as you can see here. So it's calling that on every frame, and this function basically does fulfills the same role as the get spectrum data function we looked at earlier that Unity provides for us if we wanted to interact with audio through a Unity audio source. The one I've created obviously does a similar thing but for FMOD events. Now the first thing that's happening in this function is 2 variables are being declared. One is called data and the other is called length. Now the types might be a bit unfamiliar. This data type here is int that's labeled int PTR. To be honest, I'm going to level with you. I'm still struggling to understand its role and how it works. As we move through this function, I can explain kind of how I'm using it, but it's a data type that I'm a little bit unfamiliar with in relation to Unity. From my understanding, it's basically a way of storing raw data, probably as close to binary data as we can get within C#. And what we're going to do later on is we're going to take data from our audio, the spectrum data, and store it inside of this variable, okay? uint is, I actually do know what it does. So like a integer variable, it holds numbers, basically, whole numbers. The difference is with the range that this data type can hold numbers between. An integer variable can hold any whole number between -2 trillion and whatever that says, and 2 trillion, whereas a uint variable can hold any number between 0 and 4 trillion. So the range is the same, it's just with integers we can have minus numbers, and with uints we can't, but we get an extension on how many positive numbers we can store within it. Now the reason why we need to declare 2 variables of these types is because in order to extract the spectrum data from our audio, we need to use this function, get parameter data, in association with our DSP variable, okay? Now, if I put my mouse there, you can see that the get parameter data function requires an index in the form of an integer. It then needs a variable to output the data into, and you can see there that variable needs to be of the system.intPtr type. And finally, it also needs to output a length, a kind of size of the data. And again, it needs another variable to do that, one in the form of a uint data type. Now, when it comes to DSPs and getting information from one of its parameters, we do actually have a few options. So if I type dsp.getParameter, you can see we can get parameter bool, get parameter data, get parameter float, and so on. Now, the one you use will depend on which parameter you're actually trying to access. So if I go back to FMOD's documentation and look at the DSP of the FFT type, we can see our 4 parameters again. Now, if we scroll down, it'll actually tell us what type those parameters come in. Now, we already know the window size comes as an integer, and so does the window type, or in other words, the window shape that we looked at earlier. Window type is just another word for it or phrase for it. If we scroll down spectrum data, which is the one we're now after, it just says the type is data, okay? It's literally just raw data. There is no kind of specific data type. Finally, the last parameter, dominant frequency, is in the form of float data. So that's obviously because the dominant frequency, or rather the amplitude of the dominant frequency, can have a decimal place in it, obviously. So that's why the type is a float. So that's why we have to use get parameter data as opposed to say get parameter integer, get parameter float, get parameter boolean, and so on. Now, we're only really interested in the data variable, okay? The length variable, we're only using it because we have to. This function won't work unless we output the length of the data into something. So that's why we have to create this variable. But going forward, we won't be using it much, well, at all, really. Okay, so basically, the spectrum data is stored inside of our data variable. But like I said earlier, the variable type, which is this here, is, or the data type rather, is no good to us really. This is pretty much raw data and it's inconceivable. What we need is we need to convert it into a format that we can use, a data type that we can use. Now, underneath the get parameter line, we have a variable called FFT param, which if I scroll up, we can see the data type for it is DSP underscore parameter underscore FFT. Now, what we need to do is take that data and store it inside of this variable. The reason why is because we can then use this variable to access particular parts of that data. So for example, that data within it contains information such as the number of channels that our audio is flowing through. So it could be mono, stereo, or even more. So what we want to do is take that data and store it within this variable. The reason why is because that data we've just extracted contains a lot of different information about the audio running through our channel group and our DSP. For example, not only does it contain rather the spectrum data that we want to analyze, but it also contains, for example, the number of channels it's flowing through. So mono would be 1, stereo would be 2, and so on. Using this variable and this variable data type, DSP parameter FFT, we can extract, or rather focus on particular parts of the data that we've just extracted, okay? The problem we've got, as I mentioned earlier, is that we've got this data in this awkward form, okay? Which isn't ideal. We need it in this format, this data type, DSP underscore parameter underscore FFT. God, that's a mouthful. They could have named that better. So what we need to do is some more typecasting. Remember, we need to change it from one form of data, one data type, to another. Now, I'm going to level with you here. The way we do this, I don't quite understand. I tried to do as much research as I could to work this out in order so that I can explain it to you as best I could. But there's just so little resources I could find online. And it was very hard to just work this out by trial and error. So I'm really sorry that I can't explain this to the detail and depth that I would like. But what I can tell you is, using this method here, we're kind of basically allocating a particular amount of space in the memory of our system that's running this code, this script. So that could be a PlayStation 4, Xbox, a PC, whatever. We're allocating that for our data as we kind of do the conversion and turn that data into a data type that we can use. So what we do is we do our typecasting. So we start the line with the type we want to cast the data into within brackets. Then we use this line. We write marshall.ptr to structure, okay? Now this will only work if I scroll up, if you include this namespace at the top, using system.runtime.interpop, I can't even read that word, interop, is that a word? Interop services? Oh God, I've probably just really embarrassed myself there. I bet that's an easy word to pronounce. But either way, we need this namespace for this to work, okay? So don't forget to include that. Anyway, scrolling back down, so we use marshal.ptr to structure. Then we follow it with 2 more brackets. We then add the variable that contains the data we want to convert into something usable, which is obviously our underscore data variable. And that, by the way, has to be of that system.int.ptr data type I explained earlier. Then we write type of, and again we write the data type we want to convert it into. That wasn't a great explanation of how that works. I'm really sorry, but hopefully that gives you some idea of what's going on there. We're basically converting it from this data type, which is pretty much raw data, into the specific data type that FMOD provides for us, DSP underscore parameter underscore FFT. One thing also I will say about this line is occasionally I would get errors. As you see it now, I would type it as you can see, but it would still give me an error. In fact, the error was quite specific. It would say object reference not set to an instance of an object, which is something that usually pops up when you're messing around with, well, game object instances, basically. So I'm a little bit confused why that popped up for me here. If it pops up for you, the best thing I recommend is to delete everything, basically. Delete everything, start again and re-enter it. Again, this script will be on my website, so you can copy and paste it straight into your games or your projects, and hopefully that shouldn't give you an error. But if it does, the best thing I can recommend is to just try it again, essentially. Maybe even just delete the script and type it out manually. I know that's a pain in the arse, but like I said, the only way I seem to be able to fix that error was just doing simple little tricks like that. Again, I'm really sorry I wasn't able to explain that any better. Fingers crossed you have better luck with this line than I am. And if for whatever reason you do understand what's going on here a little bit more, I would very much appreciate a comment to help me and everyone else watching this video out, because I'd love to be able to share this more with everyone. And explain a better understanding of what's going on here. But like I said, the gist of it is we're taking that data, casting it into something more specific for us to use. So now that we've got our data stored in a variable we can use, we can actually access some of our spectrum data. So for example, all I would have to do is write FFT param, the name of our variable, dot spectrum, followed by 2 open and close brackets. Now, the variable spectrum is another array. This is actually like a double array, so it's even more confusing. But this is basically what's containing our data. In fact, it's what's containing those specific samples and the amplitude of those samples. So all 256 or 512 or whatever you set your window size to. Now, like I said, it comes in the form of a double array, which is like an array within an array, a list within a list. The reason why is because with our audio, we can obviously have multiple channels. So if I go back to FMOD real quickly, you can see my event has 2 channels. It has a left and a right. It's in stereo, okay? Makes sense. Now, obviously with stereo audio, we're getting not just 1 audio signal, but 2, 1 for each channel. So they're both different, right? Which means that the spectrum of both of those audio channels are going to be different. So going back to our image of spectrum data, let's pretend that this is just what the left channel looks like, okay? And this is the result of it just taken at, say, the very first, I don't know, very first second of a piece of music playing, right? Well, let's say in that music we had a guitar panned to the left and a, I don't know, for some reason a drum panned to the right, okay? Well, obviously the signal in the left is going to be different from the right, okay? So that means that the 512 samples that we slice this up into is again going to be different from the left to the right. The amplitude of those samples are going to be different. So that's why if we go back to the script, we have a double array. In the first array slot, I guess you could call it, you need to tell this code which channel you're interested in, if any, right? Obviously, if your audio is just mono, you can just say 0, right? Because there's only going to ever be 1 channel. Again, it's indexed. So channel 1, which I'm assuming, I think is if we're using stereo, will be the left channel, will be represented by the number 0. And the second channel, the right, will be represented by number 1. And if you were, say, using surround sound, where you've got like 5.1, again, 0, 1, 2, 3, 4 for each channel, okay? But anyway, if your audio was just mono, you would just write a 0, okay? That makes sense, because there's only 1 channel, right? So we just say we were only interested in that 1 channel. However, if you've got stereo, like I said, the first channel will be 0, but the second channel will be represented by a 1, okay? So once you've told it which channel you're interested in, you then need to tell it which sample you're interested in, okay? So remember we set the window size earlier to 256 within Unity. So maybe I want to access sample number 65, right? Well, then we'd write that number in there, okay? Now, at the moment, I've just written it randomly in our script, so that's not going to really do anything. In fact, it's going to give it an error. But let's say I could declare a float variable, call it thingy again, because I can't think of a good name. And then I could set it to that specific sample. So what I've basically done, let's go back to our picture. What I've basically done there is I've taken a variable, or I've created a variable of the float data type. And I've said, right, I want you to go through all the samples, find number, well, first I want you to pick a channel. So channel number 1, which will be the second channel, so the right channel in a stereo piece of audio. Take that channel, then find sample number 65. So go through all of those samples, and let's say sample number 65 is like here, between frequencies 250 and 260 roughly. Find that sample and then give me the amplitude of that, or the average kind of amplitude, okay? Then that would end up being stored inside a thingy, okay? Now, obviously, we're not interested in just one single piece of sample. We're interested in all of them. So what we're going to have to do is do some clever things with for loops in order to tell our script to access all of the samples for both channels. Or in fact, you know, the way we're going to set this up is assume that we don't know how many channels there are and do it so that it doesn't matter how many channels there are, even if this is surround sound, we'll do it for each channel and for all samples within each channel. Now, before we do all that, there's one thing I had to add, and that is this if statement here. So I noticed in my testing that after converting the data into the DSP parameter FFT type and storing the data inside of the FFT param variable, sometimes, for whatever reason, it wouldn't recognize that data. It would just go, sorry, there's nothing there. Which is weird, I know, I don't know why. I realized in order to fix it, we had to run 2 lines of code again until it finally woke up and went, oh wait, there is data here, there is audio playing. Those 2 lines of code was the get channel function, which remember takes a variable, or rather takes an event and outputs its data into a channel, and then adding the DSP to that channel group. So these 2 lines of code here basically are exactly the same as these 2 lines of code here. We're kind of attaching everything again to each other. So we're taking the channel group, attaching it to the event. We're also taking our DSP, which now is of the FFT type, and attaching it to that channel group. And basically what this is going to do, so every frame, well, let me back up a bit. So in the if statement, I'm checking to see if the number of channels that, using the data, we're checking the data to see how many channels our audio is passing through, right? If it's 0, then that means there's no audio passing through, right? There has to be at least one channel. It has to be at least a mono signal. So if it's 0, we know there's something wrong and we can't yet access the spectrum data. So if that happens, if we check the number of channels and it's 0, then I simply run these 2 lines of code again. I tell it to get the channel group variable, attach it to the event, and also attach the DSP to that channel group, okay? Then it'll do that every frame until it finally wakes up and realizes, oh, hold on, there is channels. In fact, there's 2 because this is a stereo audio file. Once it recognizes that, it goes, right, okay, I don't need to run this if statement anymore. Instead, I can come down to this else if statement, which we're now going to talk about. So the else if statement is slightly different. Now we know that there's at least one channel, we can start pulling the sample data from it, right? However, we don't know how many channels there are. I've built this so it's designed to, well, it should, in theory, work for mono, stereo, surround, and so on. So there could be any number of channels. So in the else if statement, before I start extracting my data, I just first check to see if the number of channels that we found in that data is any greater than 1. So if it's mono or bigger, basically. And then if it is, then we can start pulling the data. Okay, now in order to understand how we're going to pull those 256 pieces of information and store them inside of the, there it is, the samples array we created earlier, which remember has 256 empty slots waiting to be stored data within, we're going to use what's called a for loop. Now, loops basically run your code multiple times during a frame, okay? So let's quickly back up a bit. As I mentioned earlier, everything within the start function happens once, and it happens on the very first frame, okay? Then everything in the update function happens on every frame, okay? It just repeats itself every frame, but it repeats itself once each frame, okay? So everything in this function here will happen once each frame. For loops, or just loops in general, happen multiple times a frame, okay? Depending on how you set the loop up. So each frame, this function is going to be called, but once it gets to this for loop, this piece of code basically is going to repeat. It's going to loop until we tell it to stop, okay? So almost imagine it like an arrow going down. The arrow goes down through the code, then it gets to here, and then it kind of circles around on itself and repeats itself until it's finished doing what it needs to do. What we're doing basically, the way I've set this for loop up is so that this loop repeats 256 times, or rather just whatever the window size is, that's how many times it's going to repeat. So in my case, 256 times. Each time it's going to take a piece of spectrum data, starting with the first piece at 0, again it's indexed, so 0, then 1, then 2, which if I go back into my picture, it will be the very first piece of sample data, which will range between roughly 20 hertz and, I don't know, 48 hertz. Then it will do the next, and the next, and the next, and the next. And it will keep doing that. Let's go back to our script. It will keep doing that until the samples array that we created is nice and full of data. So let's quickly talk about how we set up a for loop, or rather how a for loop is formatted. So just like an if statement, you write the word, well, for instead of if, and you create brackets. Now, the first thing you do is you create a variable of the integer data type. I'm pretty sure it has to be an integer. Actually, I don't think it has to be, but you'll find more often than not that people use integers alongside of for loops. And I recommend you do as well. So declare an integer specifically for this for loop. So I've called mine B, and actually, side note, I'm going to stop quickly. I'm going to change it to S. And you'll see why I've changed the name of it in a second. Okay, there we go. So I've changed it to S. So I've created an integer and I've called it S. And I've set it to, it starts at the value of 0, basically, right? That's the first part of a for loop. Then you need to say on what condition you want this loop to repeat, okay? So obviously this repeat loop can't go on forever. We need at some point to tell it to stop. And this is kind of what this does. When is it going to stop? Well, it's going to stop whenever the S integer variable is any greater than the window size. At the moment it says when S is less than window size. That's basically saying that's when the loop will run. If S is less than the value of window size, then the loop will run. In other words, if S ever becomes equal to or greater than window size, then the loop will stop, okay? So it's a condition in the same way that an if statement has a condition, depending on whether or not it will run. Now finally, we need a way of changing the value of our S variable. Because obviously if we don't change it, then the S variable is never going to equal or be greater than the window size, and therefore the loop will run forever. And that can actually break your game and freeze it, so make sure your loops don't ever break. So the way we change it is with the final piece of the for loop. We just write S++, which basically means add 1 to it, okay? So let's quickly recap. When we get to this part of our script, the for loop creates an integer variable called S, and its value is 0. Then it says, so long as S is less than the window size, which again is 256, it will repeat this loop, okay? Then for each time it repeats the loop, it will add 1 to the value S. So the first time it will start at 0, it will go through the loop. Then it will add 1 to it, go through it again. Then it will add another to it, so now it's at 2, then go for it again. And so on until it gets to the value 256, at which point it will stop looping and our script will end. Okay, cool. So hopefully by now you understand that the idea of that for loop is to go through each piece of spectrum data that we collect on every frame. Okay, that's the idea. But like I said earlier, there's a chance that we might have 2 channels or more than 1 channel with their own different spectrum data, different amplitude levels. So we need to go through each sliver, each sample for each channel, okay? And the way we do that is basically with another for loop. So this time we've created another integer called C, which stands for channel. By the way, that S stands for sample. That's why I changed the name of it. C also starts at the value of 0. This time, because we're using this to kind of check, we want this to run for every channel that we have our audio playing through. We want to check to see if C is ever less than the number of channels we've found in our data, okay? And then obviously to prevent our loop from repeating endlessly, we're adding 1 to the value, okay? So now let's quickly take a step back and explain what's happening every frame. So every frame, we get all our data, blah, 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 we do all the setup, then we get to those for loops. Now what it's going to do is first take take the sample data for, well, it's going to take the amplitude level of the first sample, okay? Then it's going, for the first channel as well. Then it's going to take the first sample data for the second channel, okay? Let's go back to our script. So we get to this for loop, it goes through all of this to get the first sample, right? Then it goes through this to get the second sample for the second channel. And then it'll do that again if there's any more channels. Then what it does is it takes this variable, total channel data, and we're going to add the two together, or if there's 3 channels or 4, we add them all together, okay? Which is what's going on here. The way we do that is we write out the name of our variable, total channel data, then we say we want to add, which is what this represents here, plus and equals, we want to add the spectrum data within whatever channel we're currently on and whatever specific sample we're looking at, okay? So let's say we're looking at the very first sample. So we go through the loop, we get to our second for loop, and let's say we're also looking at the very first channel. Let's also say this is a stereo piece of audio, okay? So for that channel and for that sample, we take whatever its amplitude is by using the FFT parameter dot spectrum variable, and we store it within this float variable we've created called total channel data. Again, by writing the C variable, which represents which channel we're after, and the S variable, which represents which sample we're after, we're able to access a specific part of the data, okay? So that's then stored in there, right? Now remember, this is a for loop, so this means that so long as C is less than the number of channels, which is 2, it's going to run again. Currently C is at 0, so now that we've come to the end of the for loop, a value of 1 is added to C and we start again. This time C is now equal to 1. So we run this line of code again, so another value is now being added to total channel data. But this time it's the value of the first sample for the second channel, okay? So now we've got let's go back to our picture quickly. Now we've got the first sample and its amplitude for the first and the second channel being added to this variable, okay? Then C is increased by 1 again, so now it equals 2. But now if we go back to the top of our for loop, C is no longer less than the number of channels. The number of channels is 2 and C equals 2. They're the same. So now this line of code won't be run anymore, okay? Obviously, if there was more channels, it would then run again. So the idea is we're collecting up all of we're collecting the amplitude level for the first sample for each channel, and we're adding them all together, right? Then what we're going to do is we want to get an average, okay? So those amplitudes could be completely different, but we just want to find a middle ground in between all those channels. We do that by taking the total channel data we just collected, then we divide it by the number of channels, okay? So this is kind of basic maths. To find the average, you add up all the data and you divide it by how much there is or how many there are. Then we simply store it inside of samples, okay? That array we created earlier. Specifically, we store it within the first slot within samples. Remember, currently in this example I'm explaining, S equals 0, meaning it represents that first slot within our array. It's the first sample, okay? So we saw that inside of samples, and voila, we finally got some sample data. We've got an amplitude level that is an average for of the first sample for both channels, the left and the right, stored within samples. Then we get to the end of this original for loop and we go all the way back to the beginning. This time, S is no longer 0, S is now increased by 1. S is still less than the window size of 256, so we go again. We create the variable again, total channel data. We go through both channels, but this time, let's go back, we're not doing the first sample, we're doing the second sample, okay? And we're doing it again for both channels. We're adding them together and dividing by how many there are, which is 2. And this cycle, both cycles, goes on and on and on. It does it 256 times until we've got each sample for both channels added together and found an average of them, okay? Then all of those pieces of data are stored within the samples array in every slot. And believe it or not, all of that happens just within, that's all that happened within one frame, right? And remember, frames happen like 60 times a second. It's kind of crazy to think how much kind of information these kind of computers can handle nowadays. Like, you don't really realize until you go through programming like this. But anyway, I'm digressing. with that, that's pretty much it. We've now been able to access all of the sample data and all of the amplitude levels, or rather an average of the amplitude levels for all the channels, and store it inside of samples. Now, we've already seen it in action, but one last time, let's save the script, jump into Unity, and let's test our scene and see those samples. There we go. So these are all the different amplitude levels as the music changes, and they're averages of both the audio coming from the left channel and the right channel. So obviously if there was instruments panned differently, the amplitudes would be different for each specific sample, so we just get an average. And yeah, all slots have been, oh sorry, no, they've not all been filled. Remember earlier, I forgot to change that. Remember earlier, I said that the window size when we, I've lost John a blank now. When we're setting the parameter of our window size, when we're setting the value of it, we need to multiply it by 2. So let's quickly do that now because we just got half the data we wanted. Then let's go back and play the scene one more time. There we go. So if we scroll down, all the channels are filled nicely. Great, awesome. And of course, this has been designed so that if we want to, we can change the window size. So let's change it to something like 16. Again, it has to be a power of 2. And let's see we can see that the array size has changed to match 16, and now we're getting 16 samples for both channels every second. Every frame, which happens like 60 times a second. Cool. Now, I know that was a long one. If you watched all the way through, thank you ever so much. But hopefully now you kind of understand. Hopefully now you understand how to extract data from an FMOD event, because now you can go on to use that to display all that data. You can take those numbers and you can turn them into, you know, changing shapes and stuff and create some really cool audio visualizers. Again, the idea of this was to explain how you can extract spectrum data from an FMOD event. So I highly recommend you go follow Pearplay's playlist, which I'll have linked, because using this, you can now basically follow on from his using FMOD, and it should work perfectly for you. Yeah, I think that's it. Thank you ever so much for watching. Again, don't forget to check out scottgamesounds.com for all the assets that I've shared in this video, all the links, and also all the other goodies I have on the website, as well as signing up to the newsletter where I share tips and tricks, updates about YouTube and stuff to the website, all to do with audio implementation. And yeah, I think I need to lie down because that was exhausting explaining all of that. I've been Henry Scott. Thank you very much for watching, and I'll see you in the next one.